Okay, section 3.2, part 2. So this is just following up after our in-class session yesterday. So we looked at energy transformation in chemical reactions, and now we're going to look at them in nuclear reactions. So this is a little bit different than anything that we've looked at so far. So one of the big ideas we need to remember with this is that background radiation exists all around us. So often we think of nuclear reactions, we think of something sort of man-made and terrifying, whatever, but radiation is naturally occurring all the time. Okay, so radiation is high energy particles or waves that are being emitted from a variety of materials. If we look back at like grade 8 electromagnetic spectrum, these are basically all the different sort of forms of radiation, not all, the majority of the forms of radiation that are just simply coming from the sun towards us all the time. So if we're looking at radioactivity, we are looking at the release of high energy particles or waves. Being exposed to radioactive materials can be either beneficial or harmful. Okay, so there's no solid rule. X-rays, radiation therapy, electricity generation are all beneficial to some extent. I mean, obviously, if you're an X-ray technician or you're not actually in the room exposing yourself to X-rays over and over and over again, but obviously the benefits outweigh the costs of it if it's a one-off kind of thing, like you broke your leg, you want to see where the break is. On the harmful side of things, high energy particles and waves do damage the DNA in our cells. And so we can get like radiation poisoning or whatever. It's actually from the DNA being damaged. Okay, there is a video here that is taking a look at the effect of harmful radiation on the body. It's actually really interesting. I highly recommend you take a couple minutes and watch it. I will have it linked just on Teams so that it's easy to find there as well. So when atoms lose high energy particles and waves, you can end up with ions being formed or new atoms altogether being formed. The high energy waves and particles are considered to be radiation once they leave the atom. So while they're still part of the atom, they haven't radiated away from it, therefore they're not radiation. Okay, so radiation is everywhere. It can be really difficult to detect because it is invisible. It's not something we can see with our eyes. X-rays were called X-rays by Röntgen well over 100 years ago, and it was just because they were previously unknown. So it's the same way we use X in algebra to represent the unknown variable. It's X-rays because they were the unknown. Becquerel, a year later, basically recognized uranium also emitted this sort of invisible energy. And it's because photographic film was actually being exposed when it was in the presence of these rocks. The Curies, so Marie Curie and her husband Pierre, so also once again looking in the 1890s, named this energy radioactivity. So early discoveries of radiation all basically relied on photographic equipment. So being on photographic plates, if you can picture like the super old school, like first cameras where the film was like a big giant plate that they needed to put into it, then yeah, like that's basically what they were using. Marie Curie is sort of one of the first most recognized female scientists, which is pretty cool. So curium is a element that's named after her. She named polonium after Poland because that's her own country. So this is one of the first sort of female scientists to be widely recognized in Western science, which is kind of worth something. Later, so the Geiger counter, the Geiger-Müller counter, was developed to basically help more precisely measure radioactivity, so that it wasn't just like, let me put this photographic plate down and then see how many lines and dots I get on it. It's in a couple of videos that I'll have linked. They're both really short. I highly recommend taking a look at them. So isotopes are one of the sort of more important things to take a look at in nuclear reactions and in radioactivity because some isotopes are more stable than others. So isotopes are different atoms of the same element, and the difference between the two atoms is the number of neutrons that are present in the nucleus. So remember that the number of protons is what defines the element as the element, and then the neutrons kind of add mass to it, but don't do anything for charge because they're neutral. So isotopes always have the same number of protons, and the same number, and therefore the same atomic number as each other, because those two things are exactly the same. But if it's one element, it's always going to have the same number of protons. Okay, so there's 3 isotopes of hydrogen. So protium is what we normally think of as hydrogen. It's just 1 proton. Deuterium has a mass of 2 because it's 1 proton, 1 neutron. And then tritium has a mass of 3 because it's 1 proton and 2 neutrons. 2 plus 1 is 3. If you look at a periodic table, your periodic table only goes to 1 decimal place, so it's 1.0 is the mass of hydrogen. Other ones go to more decimal places, so you might see 1.01, and that 0.01 is coming from the existence of these other isotopes. So because they have different numbers of neutrons, isotopes have different mass numbers. Isotopes of an element have the same symbol and the same atomic number, so nothing else has changed. But looking at the mass number refers to the protons plus neutrons in an isotope because those are the things that are providing mass. Okay, so the atomic mass, which is that number that shows up on the bottom of the periodic table, is a proportional average of all of the mass numbers for all of the isotopes of an element. Okay, so for example, if you look at boron, boron has a mass of 10.8 on the periodic table. 19.9% of boron atoms have 5 neutrons, and 80.1% of them have 6 neutrons. So all of them have 5 protons, okay? So there's our 5 protons. But 20% of them, roughly, have 5 neutrons, therefore an overall mass number of 10. And then 80% of them, roughly, have a mass number of 11. Okay, and then if you go through and you just sort of proportionally work that out, so 20% of 10 plus 80% of 11 gives us 10.8, which is that number that shows up in the periodic table. Okay, so 20% of them have mass number 10, 80% have mass number of 11. Okay, and then what mathematically what that looks like, so 0.199, so that's 19.9% times 10, plus 0.801, so that's 80.1% times 11 equals 10.8, which is then our atomic mass that we see on the periodic table. So mass number is referring to an individual atom, and then atomic mass is referring to that average in proportion. Okay, so because we do have different isotopes, it is really important that we have ways of identifying them. So we use standard atomic notation in order to do this. So we include the chemical symbol, the atomic number, and also the mass number. So what this would look like for potassium, for example, if we wanted to look at the first isotope, potassium-39, we would have the chemical symbol, the atomic number, which for potassium is 19, and that never changes, and then the mass number would go up the top. Okay, so that's our standard atomic notation for potassium-19 in this case. Potassium does have 3 isotopes, as I've said, potassium 39, potassium 40, and potassium 41. So your mass always comes from protons and neutrons. So the number of protons, 19, 19, 19, never changes because that's what makes it potassium. Okay, but 19 plus 20 is 39. 19 plus 21 is 40. And 19 plus 22 is 41. So those two numbers added up, the number of protons in the nucleus and the number of neutrons in the nucleus, give us our isotope number. Okay. In nature, there's a particular ratio of potassium that we find. So 93.2% is potassium 39, 1% is potassium 40, and 6.7% is potassium 41. Okay, so if we go through and work that all out, okay, so percent times mass plus percent times mass plus percent times mass, that gives us a 39.1 that we see there. Okay, so this is that's the average. Okay, tons of things are naturally radioactive. So bananas, really high in potassium. Because they're really high in potassium, potassium has different isotopes, some more stable than others. Bananas are radioactive. Okay, so potassium often undergoes something called beta decay. Potassium 40 is radioactive, and it is in bananas. Okay, so a chunk of uranium ore has the same much radiation as a bunch of bananas, which is kind of crazy. Just different types of radiation. Okay. Radiation exposure in daily life. So it's got kind of a breakdown of where things come from. We're not going to worry too much about the microsievert and what that means and whatever. But so different places you might get it. So if you had an X-ray, that would provide some of it. Being in kind of any plain old regular public space, so just simply out in the open, other people around, whatever. Different types of X-rays. Nuclear power plants, we don't use them here, but Eastern Canada uses them all the time. Taking a plane, okay. Yeah, so different types of food, all kinds of different sources. Okay, and then there's a few questions here for a reading check. And then also some practice problems. I have uploaded into the files section of Teams. I've uploaded these 2 slides as just a Word document, so it gives you an opportunity to find it there and work through it.